Hello, everybody. Welcome to Chem 1115, Chemistry and Society. This is our lecture video for the notes packet for Chapter 7. And as I always say, please make sure to also go read the full chapter and in addition to reading these notes. And then I make reference to a couple other videos in this lecture that you are also going to need to go watch on my YouTube channel or also embedded in Canvas. All right, so in Chapter 7, we're talking about alternative energy. And here are some guiding questions to get us started. How much energy do we use? And then what are some of these other alternative energies? And so this is your reflection. I'm gonna skip over that for you to do for points. So sources of electricity are kind of displayed here in this chart, just a rough estimate of where we're getting most of the energy. I'll let you look at that on your own. Here is the general method for how electricity is produced. And I say general because all electricity production methods, with the exception of solar, follow the same basic format. So I wrote something turns a turbine. We'll get back to what that something is in just a second. Then that turbine is attached to a generator, and then a generator makes electricity. Now you might say to me, Dr. Brock, what's a generator? Well, you don't really need to know the ins and outs of the mechanical engineering behind what a generator is. But let's just say for the purposes of this class that it is a machine that makes electricity. Generates electricity, hence its name. And a turbine is just like a big, it kind of looks like an engine. You know, like if you ever look at a plane engine, you know, it's got all those blades that spin. That's kind of what a turbine looks like. So what is the something that turns the turbine? Well, it depends on what kind of electricity production method we're talking about. If we're talking about a coal power plant, we burn some coal, that heat boils water, and then the steam turns a turbine. If we're talking about a nuclear power plant, some sort of nuclear reaction occurs, and then that heat boils water, which makes steam, and the steam turns a turbine. If we're talking about a hydroelectric power plant, falling water turns the turbine. And if we're talking about wind energy, then the wind just directly turns blades connected to a turbine. Now, solar energy is different, and it'll be on a separate page. So here's a figure from your book. You've got potential energy turned into kinetic energy, turned into mechanical energy, turned into electrical energy. So just FYI, as we mentioned in the last lecture from Chapter 6, coal-fired power plants are not considered alternative energy, but I've included them in the Chapter 7 notes just as a comparison because they all follow the exact same general format. So if you understand how one works, you're basically going to understand them all. All right, so in a coal-fired power plant, you've got your coal being burned. The heat heats the water into steam, which turns the turbine, and the turbine is attached to your generator, which makes your electricity. And then that steam goes back down and gets condensed and goes back into your boiler, or it goes out into a cooling pond and then goes back in, depending on its temperature. So there is a lecture that I have on the YouTube channel and also in Canvas called Alternative Energy Mini Lecture. And it goes through each one of these methods of energy production too. And then I bought a little kit and made little videos. They're like 1-minute videos of me showing you how a solar panel works, of me showing you how a hand generator works, of me showing you how a mini hydropower plant works. And so go check those out. They're very short. But this information about alternative energy and how it works will be on the Chapter 7 quiz, and it's also on exam 2. All right, let's move on to nuclear power. So nuclear power, just like coal-fired power, is just instead of burning coal to heat your water, to turn your turbine, to turn your generator, you are just carrying out a nuclear reaction. And you're controlling that very carefully, obviously, because it's a nuclear reaction, as opposed to a nuclear explosion where it's not controlled and the energy just goes everywhere. So here's the same figure. Notice, look, the end product is the same. The only difference is here you've got a nuclear reaction that heats the water into steam, And then it's all the same. Steam turns the turbine, which turns the generator, which makes your electricity and goes out. All the rest of this is just how to cool down that water because it's going to be really hot. So you have your cooling tower, then the lake of some sort, and then it goes back in and then it's back in your reservoir. So if you're talking about a nuclear power plant, you're using a uranium fuel source, and they're about the size of a dime. And then they are put into rods like this, big long rods, and they are in a bundle, and then they are put down in here, and it's controlled that way. So let's talk a little bit about radioactivity, just in general, while we're talking about nuclear. What are some sources of radioactivity in your life? Naturally occurring is the answer to the majority of our question. Radon that exists in our environment, and then other natural sources other than radon, that accounts for the vast majority. Then where else can you be exposed to radioactivity? Well, if you go get an X-ray, if you're doing some sort of nuclear medicine, and then consumer products, and then this tiny little percent is everything else. And you have natural radiation in your body just from radioisotopes. That's just part of our existence as creatures. So here's a chart that kind of gives you an idea of how much radiation you can be exposed to and what would happen. So 0 to 25, you have no effect. Then it goes all the way up to a dose of greater than 500 rem, you would be dead. All right, so you can read over this on your own. Most of us are always in this range down here. But the thing about radiation, the thing about radioactive waste is that it's around for thousands of years, because some of these take thousands of years to decay. And so they are dangerous and hazardous to have around for a long time. That's the main downside. If you were going to list the pros and cons, that's one of the big cons for radiation, because it takes a long time to go away. And so many of you have heard of the Chernobyl disaster in 1986. It occurred in Russia, and it was a complete disaster. The control rods failed, and the safety measures failed, and 9 tons of radioactive material, that's 100 times more as a bomb, just went up, and it carried it all over Europe, and it was really great catastrophe, very bad. So you're not going to have to memorize the chemistry behind what happened there, but here's a little link that you can go check out if you're interested in learning more on your own. And so the consequences of that, lots and lots of injuries and deaths and people being evacuated. And then unfortunately, because of the fact that it was launched so high, it went all over, 250 million people exposed to this radiation. And then the estimates of future cancers from that range from anywhere from 7,000 to 1 million. That's a huge range, and it's obviously going to be difficult to measure that over the years. But as a result, there's radiation in the environment, and then a lot of people are scared of radiation now because of that, and rightfully so. I mean, that's something scary. It also caused people not to trust their government or worry that things were going to be covered up, and people are just generally uneasy about the idea of nuclear power now. So what's the future? Well, it's definitely got to include a lot of safety measures, obviously. It's got to include a lot of gaining the public trust. And then it's got to just make sure that we have everything in place to keep everybody safe. So I like this picture right here of this guy. He's trying to plug in this lamp of some sort. Am I going to plug into solar? Am I going to plug into hydroelectric? Am I going to plug into nuclear? I don't know. Need to pick. Right, but we have regulations here in the United States, and they are supposed to be inspected, and they should make sure that there's always a backup so that we don't have meltdowns. But I mean, you should have good, safe science no matter what kind of science you're doing, even if you're just doing an experiment in your kitchen with your goggles on, right? You always should have safe science. All right, let's move on to wind. So in the wind situation, which is considered a renewable energy source, the wind is attached directly directly to it. So it's a lot easier to deal with. Your generator's back here. Your turbine's a lot smaller right here. And so your turbine is little, and it turns the generator. So it's just directly right there. And so your wind power is going to be based primarily on where you live. The blue states have the most, followed by your orange states, your green states, and then these pink and white ones have virtually none. And it's just based on where you live. And here's a graph of average wind speed if you're curious. All right, let's move on to hydroelectric power. It has been increasing dramatically since the 40s and 50s. But it's created a lot of electricity since 1990. That's the line here at the top if we're looking at the renewable sources of energy. So here's how a hydroelectric dam works. You have water in some sort of reservoir, and then it falls down, turns the turbine, which turns the generator, which makes your electricity. And then the water is released back into the river. So some of the cons of the hydroelectric would be you obviously have to build this gigantic dam. You have to be pretty invasive in the environment, right? So the fishies and the frogs and the turtles and all of the other creatures that live in the river are obviously going to be affected by this. And it requires a great amount of flooding too. You have to flood large amounts of area of land in order to make the reservoir. And then there's also risk of, flooding in other parts of the river as a result. So again, anytime we're talking about these sources of energy, you always have to consider the pros and the cons. And then the last one we have is the solar power, and it works a little bit differently because there is no turbine, there is no generator. That's the only one that is turbine free and generator free. It works a whole different ball of wax. So here's what happens in solar power. You have this matrix of silicon atoms. And as we've talked about in the past, what happens when light hits an electron? Well, the electron gets excited, right? It starts bouncing around, woohoo! And so that electron moves, creates a hole, and then creates further electron. And then if you just can harness that over a large area, you've got all these free electrons. And what is the definition of electricity? It is the flow of electrons. All right, so what should I know for a quiz or a test with regard to these things? You need to know that general method for electricity production, be able to list the pros and cons for each one of these, be able to explain the something, right? So is it moving water? Is it moving air? Is it heated steam? What is it that's turning the turbine or the generator? Or in the case of solar power, how is it that that's being generated? Well, your electricity comes from the fact that as these electrons get excited, they break loose of this electron matrix that they're living in. And then you need to be able to make an argument for which method is your favorite and be able to defend that. So that's where we're going to stop. Please make sure to go watch the other videos on the YouTube channel or in Canvas. If you have any questions, please feel free to reach out to me. And I hope you have a good day.